I hope you got the introduction. So my name is, well, that I spoke on the slide. Anyway, so my name is Alan Sommerskog. I live in Stockholm, where I work as an independent consultant. I've been an MVP for many years, SQL Server, and I have a website, sommerskog.se, which you could say, I will try to put back the camera because I still like to be seen. Sorry. Oh, this is really good amateurish. Oh, anyway, so I have a website, sommerskog.se, which you could say is a small collection of large articles, but this is not any of those articles. I'm trying to plug in back my camera. Let's see. Connect to the host, and we'll see. Maybe I will forget this. Use new. And it's using the, yes. Now it's using the integrated camera.
I don't see. Yes.
Yeah, I'm back. Let's see how long the picture will be there. My email address there is there, sq.sommerskog.se, in case you have any questions about this presentation that you don't get answered right now. Please feel free to contact me. I'd like to point out that slides and scripts, they are available on my website, sommerskog.se/present. So if there's something you missed, I'll move on too fast. Don't worry, you can get everything afterwards. So what I'm going to talk about is, well, the first thing I will talk about is two scenarios where we like to use chunking. So the first one, I've purposely labeled it a little bit cryptically here. Don't bite off more than you can chew, and be nice to others. Then I will talk about how to implement chunking, and that will be the major part of the presentation. I will talk about performance and other pitfalls, things you have to think about. The last thing I will talk about is another scenario where chunking comes into play. That's for error handling. Here with the cryptic subtitle, when all or nothing is not what you want. So say this, you have a table and you want to perform an operation on that, well, entire table, or at least the better part of it. So may, for example, it turns out that the table has an integer ID column, and you looked at that ID column, oh, there's 10 digits in it. Oh, we'll soon hit the roof, and so we need to change this to a bigot. And of course, you can do that with all the table. But you may decide that, no, I will create a new version of that table and copy all the data over in a single insert statement. Or it could be that you have added a new column, a nullable column to that table, but now you want to initialize that column for all rows by taking data from somewhere. Or it could be that you want to do purge operation, like getting rid of 50% or 90% of the rows in that table. Now let's say that this table has a size of 300 gigabytes. What would happen if you would try to do that in a single operation? Hey, it could be a lucky day. Everything could go just fine. But it's not unlikely that the transaction would start to grow violently and maybe even outflow the disk. You could also get problems with temp to be, both the data and the log file, because, well, maybe your operation requires you to fill temp tables, and they get really big as well, or there are query operators like in the plans, like spool operators, sorts, hashes, etc., that spill the disk. Memory can also be a problem with a buffer cache, because let's say that this table exceeds the available memory with some factor. If you're only going to do a single scan, it's not a problem, because the SQL Server would read the row, update it, and eventually it will fall out of the cache as it has to read new rows. But if you have to get back to the same row multiple times, well, this means that, well, you will be reading it from disk multiple times. That's not good. And yet another problem is if, well, you have to cancel operation. And if it's a really one big operation and you cancel it towards the end, the rollback is going to take a very long time. Now, the remedy to all of these problems is to split up the work in chunks. So rather, you don't go back to what you want to do as a very young SQL person, do one row at a time, but nor you're going to do everything at once. You're going to do it in loops, but in sizable chunks, subsets of the data. And of course, the chunk size should be small enough to avoid problems with the log file and temp to be. But this is important. Don't make the chunk size too small, because the chunking will add overhead, and bigger chunks are more efficient, as long as you don't hit any of those limits. Now, the obvious question there might be that, well, so what is the right size? How many rows should I have in my chunks? You know the answer already. It depends, of course. It depends on a whole bunch of things. First of all, what is the current size of the log file intended to be? Let's say we have this 300 gigabyte table, and the log file is already 10 terabytes. Well, then the log file might not be a problem. But also, don't look at only at the number of rows. Don't overlook the size in bytes. Let's say that this table only has 1 million rows. But there is a lob column in that table that you're going to work on, and it has an average size of 1 megabyte. You are looking at a 1 terabyte table. You probably need to work with that one in chunks. Now, and well, still, I have a standard value. It's kind of 5 million rows. But as I said on the slide, your mileage may vary. This value is not entirely taken out of thin air. A couple of years back, I was working with, I had made a change to a table, added some columns and altered some data types. So I wanted to copy all the data from the old schema to the new schema. And it was a fairly wide table, 4 to 5 rows, but not in the lobs in it. And I had actually a program that generated these kind of loops. But I wanted to try what was the good chunk size. And I found when going from 500,000 rows to 5 million rows, I still gained performance by, let's say, 10, 15%. I did stop at 5 million rows because beyond that, it gets too much. But as I said, your mileage may vary, and this is just sort of a very rough estimate. All depends a lot on the operation. Now, I like to talk about the transaction log, because even if you split up the work in chunks, it doesn't matter. You're still going to produce a whole lot of transaction log if you're going to operate on a 300 gigabyte table. Now, there is one simple way out. Put the database in simple recovery and let us conserve just truncate the log. Now, this is very, very rarely a good idea to do in production. You might be tempted to do it, but keep in mind that if you do this, you will break the log chain, and it may turn out that you already had corruption in the database. So what you really needed to do was to go back to an earlier backup that was clean and restore logs, and you broke the log chain, so that you lost that option. Now, I absolutely recommend doing this for production purposes, and if you're in availability, you can't even think about it. So if you are in full recovery, what you need to think about is increasing the backup frequency. Because if you, let's say the transaction log is being backed up like every 15 or 30 minutes, you may very well with your chunking script still explode the log in those 50 minutes. So increase the frequency to, let's say, one per minute, every minute. You might think, couldn't I just add backup log to my chunking script? Yes, you could, but only if you write to the same place with the same min convention as the schedule log backup, because else, if you write the logs elsewhere, then someone else is going to pick up those logs. It's going to cause a confusion. Now, what I've talked about so far is a scenario where you more or less have the database to yourself, really large operation for, like, let's say, schema change. But be nice to others. Well, this is a different scenario and probably a smaller operation, maybe only 5 million rows in total. But now you are in a live system, so you may impact other users. Operation could take up, if you did it as a single operation, you could take up too much resources in terms of CPU and memory, and moreover, you could cause blocking or deadlocks. And again, the remedy is to split up the operation in chunks, now with a fairly small chunk size, which means that your operation will be less efficient, but the overall system health will be better. And in this case, there is a kind of a magic number. Not, I say kind of, because it depends exactly where the problem is. But often when you do this, you may want to avoid table locks. Because let's say you're doing a purge operation and you're going to purge very old rows on the left side of the table, and users are mainly working at the right side of the table. Now, you don't want to block these users over here, so you want to avoid taking a table lock that could block these users. So one way you can actually test this. How many rows can I actually take in my chunks? So you can do a test operation and do it inside a transaction and inspect the logs in system tran logs. So let's have a look at that. What I mean by this. So here, I got, the database for today is called BigDB, and one table we're going to work with is called BigTrans. We're going to talk more about that later. Here I'm doing delete top 2,500 rows, and then I'm looking in system tran logs. I'm looking at resource type. What sort of thing am I locking? In what way am I locking it? What kind of lock am I taking? The ID for it, and if it isn't table name, I try to translate it, and how many locks did I get? So I'm going to run this, and then I do a rollback transaction. And you see, first of all, I got a shared lock in the database. Then I got the key locks. I got 2,500 of these. These are row locks. So those are good. I got row locks. I did not lock the entire table. Oh, wait, there is an object, BigTrans. So I did get the log on my table. Yes, but this is an IX log, a so-called intent log, which means, well, it's an intent log is, hey, I'm down here doing work. So this means that I do actually have real locks down here. It will block anyone who's want to take a share lock on the entire table, but it's not going to block the writers or readers over here. And also get intent locks on the pages. Now, maybe I can take a little bit bigger chunk size, I think. I'm going to try 3,000, because after all, the magic number was 5,000, wasn't it? No, this did not work out. There were 2 locks, one on the database, and 1 big fat lock on the table, because in total, there was 2 indexes. So that's why I got more than 5,000 locks. So 3,000 was too much for me. 2,500 was the sweet spot in this case. So when you do this test, just repeat, you should only see X-lock on key or read resources. Key, those are index keys, and read, that is when you have a heap. If you say X-lock or log X-locks on object level, well, then you have your 2 big chunk size. If you say X-lock on page, or it could be that your index is not really good, and the SQL Server decides, now I'm going to try locks on pages instead. But you need to work with something if you see X-locks on pages. Intent locks on object or page, they're okay, because they're only indicating, hey, I'm down here somewhere. Now, let's talk about the challenges of doing chunking. It's not that chunking isn't really like a wide adventure going on a multi-day hike. You need lots of equipment, emergency contacts, lots of food, etc., etc. No, but it's not really a walk in the park either. It's kind of like a forest walk. You need sturdy shoes. You might have to negotiate a stream or two. You could slip on a stone. You could trip on a branch. So first of all, you need to write more code, which means that's more code that can have bugs. There's more code that you need to test. And you need to think about, how is the application? And what if the workers interrupted halfway through? How to deal with this? And most of all, performance. If you do chunking wrong, the chunking can have such a bad impact on your performance that it would have been better if you hadn't done chunking at all. And I will elaborate these things in more detail, more or less going in the reverse order than they are on this slide. So let's start talking about performance. So here's the first chunking operation for today. So I'm saying here, what I want to do is simply, I've added a new column to my sum big table. And what I'm doing here, I'm setting the chunk size to 5 million rows. And I'm keeping on looping as long as I'm updating 500 rows, saying update top chunk size, some big table, new column, some value, which some value could be a subquery, or I'm getting values from somewhere, it doesn't really matter. When new column is null, and I capture the row count. Now, well, hang on, so let's see, yes. So I want you to think about for a few seconds, is this a good chunking operation or not? I'll add some water when you consider that. No, this is not a good chunking operation. So the first iteration, it would be quick, because SQL Server will quickly find 5 million rows where the new column is null. Great. Now, then next time, we're going to come back to this, SQL Server is probably going to scan the clustered index and find, okay, the first 5 million rows, okay, new column is null. Oh, here's 5 million rows again. So it's scanning 10 million rows this time. Next time, it's going to scan 15 million rows. Next time, 20 million rows, etc. We could avoid that if we index a new column, but then we have to do the update. We have to maintain that index. That is also not very good. We don't, most of the time when you do these operations, you want to add indexes afterwards when you're done. So the key here is that indexing is critical. You must always define your chunks so they go over an indexed column, because else you will scan that big table over and over again. Let's say now that some big table that the chunk size was such that it will lead to 500 chunks. This means I would be akin to doing 250 table scans, because each scan will be longer, longer, longer. And one scan, you have to do one scan because you're going to work with all data. But 250 scans, that is going to take way too much time. So also, I would say this, the larger your chunk size is, the more imperative it is to use the clustered index. Because now let's say you're going to loop over a non-clustered index, and the optimizer looks at this and saying, wait a minute, that's 5 million kilograms. That's goddamn expensive. I'm going to scan that table. No. So the clustered index is really appealing. For smaller chunk sizes, yeah, the non-clustered index may work, although again, it's still 5 million kilograms, which is kind of expensive. But I need to qualify this, because there might be business logic that requires to do your chunking a certain way, or you could be joining to other tables that could change what index you're going to use. And we're going to see an example of this, of the latter thing later on. Now, this table, big trans, I like to talk a little bit about it. I got this originally from Adam Mechanics. He had a blog post called Big Adventure Works, which I used. It has 31 million rows. It's the size of 2.2 gigabytes. Quite big to be a demo database, quite small to be a real-world database. It has 5 columns. There's a transaction ID, which is a primary key. There's a product ID, which is a foreign key to another table, and 3 more columns that are all available. And there is a non-clustered index on product ID, transaction date, including the other 2, amount and quantity, and implicitly also this one, because that's the clustered key. Now, I want to do some changes to that table. I think my business is going to grow, so I need big int here. And then I think, oh, wait a minute, I'm going to clean up those data types here, and also going to make them not null. So how can I do this? Well, of course, I could try all the table. And I'll try this, but because I'm changing the primary key, I need to drop the primary key and the non-clustered index and recreate them at the end. And I need to run 4 of the table, all the column statements, all of them rebuilding the table because I'm doing size of data operations. So yes, that wasn't very fast. It took 984 seconds in total, and the transaction log grew by 20 gigabytes, starting on 700 megabytes. So I decided, no, maybe I should do this. I created a table called new trans, where I have the clustered index in place, but not the foreign key in the non-clustered index, because I found that it was more efficient to add those what I've done. So I first copied all the rows in the single insert statement, created the foreign key in the non-clustered index, and yes, this was fast. It took 6 to 8 seconds, and the transaction log now grew by only by 7 gigabytes. Now the question is, can we improve this by doing chunking? Well, I'd like to introduce you to a generic way to drive chunks. Now, so here I have a stored procedure with a chunk size as a parameter. Wait, yeah, that is actually necessary, not a token of best practice. The reason I have a stored procedure and have a parameter is that I ran a bunch of tests to try different chunking techniques, etc. So it was a lot easier to package those as the procedures and use a parameter. But if you're going to do, well, let's say like this here, a table change, you're not going to write just a procedure, and you might even hard code the chunking size, and that's perfectly okay. It's what's inside though is what I like to show you. So min ID and max ID, those are the lower and upper boundaries for my chunks. I'm going to set the min ID, the first lower boundary to the smallest transaction ID in my table. I'm going to keep on looping as long as this one is not null. And then I'm going to have this subquery, select top chunk size transaction ID from big trans, where transaction ID is greater than my lower boundary or my transaction ID ascending. And then I get the max value out of that, so I get the upper boundary for my chunk. And then I simply do an insert select from big trans where transaction ID between these two. And when that insert has completed, I get the next lower boundary by taking the smallest transaction ID, which is bigger than my current upper boundary. And I keep on looping, and when this one returns null because there was no more data, I'm done, and I recreate the non-clustered index of the foreign key. Now, before I go on, I like to dwell on this pattern a little bit, because this is quite interesting. Now, as it happens in this particular table, the big trans, the transaction IDs are perfectly contiguous. So you might think, well, it would be easier to just say at max ID is equal min ID plus chunk size minus 1. And yes, when I did this for the bigger chunk sizes, that was like, well, 5–10% faster. Interesting enough, and I don't understand why, for the smallest chunk size, it was actually faster to doing it this way. But the more interesting thing is that this pattern also works if there are lots of gaps. If I do the thing with plus, the naive thing, well, if there are lots of gaps, maybe one chunk will only have 3 rows. That's not very good. So this one guarantees that I will have the same number of rows in every chunk. And not only that, but let's say I don't have an integer column. I have a string column, or a date column, or a GUID column. This pattern works with any indexable data type. And not only that, it even works with non-unique keys to some extent. I'm going to talk more about that one later on. Now, so how did this go in performance? Well, here is some data. First of all, I'd like to remind you that all the times you see here includes restoring the foreign key and non-clustered index. I did it that way to sort of mirror a real-world case. And you can see here that, yes, the smaller chunk sizes, I really have to pay a penalty for these, although we're going to see later how we can improve this. But it was really not good using these smaller chunk sizes. We can also see this, as long as I keep the chunk size, well, up to 1 million rows, the log doesn't grow, except for the smallest chunk size. For some reason, it grows a little bit. But here, for 6 million rows, it starts to grow, and for all rows, as I said, it was 7 gigabytes. And, well, of course, this is not extremely clear, but you can see here, for 1 million rows is kind of the sweet spot. It's the fastest one in the bits. So here I got, because this was the highest chunk size where the transaction log did not grow, because Probably what I'm paying for here is exactly growing the transaction log. Now, I'd like to remind you, this is only 2 gigabyte table. In a real world scenario, you wouldn't dream of doing chunking on such a small table. You would do it all at once. And also, this is data from my laptop. Your testing may yield different results on different hardware, etc., etc. Now, there's one thing I haven't talked about yet, but we need to consider. The optimizer has no idea about this value of these at min ID and at max ID because they're local variables. So it will make a blind assumption about the hit rate. Now, of course, you might think for this simple operation, it doesn't matter. But let's say, am I doing a more complex thing where I'm joining to other tables? It can have quite a bit of impact on performance. I actually ran into this a couple, well, was it 2 years ago now? I don't remember. But it was, anyway, I was working with my client and I had a table that I wanted to change, add some more columns to get initialize those columns with data from other tables. So I wrote a script. It was, well, I had the tools. Chunky was built in for a chunk size of 5 million rows. But in my test table, I only had 20,000 rows, so there was no problem. Eventually, my client sent it out to their customers. And while in their test environments, thankfully not production, it took, well, 12 hours at one site, and I think they gave up of 24 hours at another site. And I thought, that wasn't very good. What am I going to do with this? And I was not working very much with that client anymore. But before I came around to look at it, another smart guy there suggested, use optional recompile. Bang, that was it. Because now with optional recompile, the optimizer knew exactly the values of min ID and max ID and could make a lot better choice of the plan rather than doing the blind assumption. And now it ran, well, I think it was 20 minutes. Now, this is okay for a chunk size of 5 million rows because let's say every chunk takes, but I don't know, let's say that it takes, a second to process. And it only takes, let's say, 50 milliseconds to compile every time. That's 50 milliseconds, you can accept that. But let's say you need to do a small chunk size. Now, maybe 1,000 rows, maybe that only takes 50 milliseconds to process and 50 milliseconds to compile. Now, that's very expensive then to do optional recompile. But there's another option. You can push those parameters, make this parameter sniffable by pushing the operation to the inner scope. So they're parameters and optimizer can sniff those. So for example, writing an inner store procedure with the whole thing. Now that sounds a bit maybe, well, extra store procedure for that kind of operation doesn't really sound attractive, but you can do it this way. Just wrap the operation in dynamic SQL. So it's a static SQL statement, but now min ID and max ID are parameters. So the optimizer, the first time that runs this, the optimizer can sniff the input variables and say, oh, okay, is that many rows? Okay, I'm going to go use this plan. And then reuse that cache plan for the rest of it. And hopefully that is good enough. Now you might say to yourself, wait a minute. In this case, it doesn't matter because there's no plan choice here. This is a class of Linux. Optimizer can't go wrong. This can't have any benefit at all. Yeah, I thought so too, but look at these numbers. I got a drastic improvement with dynamic SQL. I slashed the execution time with a factor of 3 for the smallest chunk size. And why? I don't really know, because there's no difference in the plan. But maybe there are some memory allocations, something we don't see in the plan that affects all this. We can also see I got an improvement by using optional recompile, but because I have to pay a penalty for the recompilations, it's not as good that for 5,000 rows, it's even slower than not doing anything at all. And then I got a problem here because it's still taking a slower time for the bigger chunk sizes. Now, for 6 million rows, that's only 7 compilations. And no, every compilation is not taking 2 seconds. I looked at the plan and there is a small difference, apparently an attempt to optimization, but yeah, it backfired. Those happens things with cost-based optimizers. Now, so this is the data that I did have running these tests on 2 occasions. When I first composed this presentation at the beginning of 2019, I was running these tests in 2016, and those are the numbers you see here. Then I ran new tests last year on this for 2019 because I was presenting this at PASS, and I did not get exactly the same numbers. They were not equally startling, but it was still a difference. I think here I got 145 milliseconds, and this one was, well, 105, so somewhat slower, but it was still a benefit of doing dynamic SQL to get better speed. But there can be small problems. So here's a different operation. So I got a table here called big orders, and I've decided I'm going to add a column to that table called total amount, which holds the total amount for the orders. So I take some of the product rows or the details rows from the big details table and add a discount and add the freight. Now, this is probably not a very good database design, but this is not a database design session. The big orders table has 5.1 million rows. 1 gigabyte in size. The big details table has 50 million rows and 3.8 gigabyte in size. And I did the same test with the same kind of chunking loop and with option recompile, with dynamic scale and nothing at all. And here are my numbers. And for the smaller chunk sizes, now dynamic scale is a lot slower. That got me surprised, had me scratching my head. What was going on? But eventually I found the answer. Turned out that for the big trends table, my statistics had been created with full scan, so they were perfect. But here I had sample statistics, and the lowest ID in the history was 13,063. This means that for the first chunk for dynamic scale, well, the entire chunk was outside the histogram. So the optimizer thought, oh, one row, and used the plan for 1 row, which was not good for 1,000 or 5,000 rows. Once, and for option recompile, the same thing happened, except it only happened for the first few chunks. Eventually, it got inside the histogram. Now, once I got in within the range of the histogram, the optimizer made a better choice, and I got, in this case, better performance than not doing plain at all. That's doing nothing at all. So I did gain a little bit here. Now, there is a workaround, possible workaround here. I can do update statistics. With full scans, I get perfect statistics. And these numbers you see here, including that operation. So now you can see the times are in par. It's not really an improvement, but at least better. But they may not always be feasible. And if you do this, be very, very careful about this. Only do update statistics on the index you will use in the chunking operation. Because let's say this table has 20 columns and there's auto statistics in all of them, and most of these columns are not indexed. Each of those columns will be a full table scan. No, you don't want to go there. There's no need to. Only do it on the very index you're going to use. But now I'm going to like to show you what's the real point of using dynamic scale option recompile. So this is the same operation as the previous slides, except that the orders table has changed. Now the clustered index is on the custom ID, and the primary key, the order ID, is only non-clustered. Look here now, I've tried looping both over the custom ID and the order ID. If I have nothing at all, it's a complete disaster. Rather than taking 96 seconds, or maybe 96 minutes if it had been a bigger table, it takes, well, 4,300, which means, well, if it had been minutes, that's several days, rather than just 1 hour and a half. The same here, well, here's it's a little better, but still, that's still more than one single day. So that's the real key of using recompile dynamic scale. It protects you against complete disaster where things just get awfully too slow. In passing here, we can note also, you might note here that looping of the order ID, the non-clustered index, you can see here, it is slightly faster than using the clustered index. And the reason for this is that the big details table still has its clustered index on the order ID, so we're better aligned with that table. I see there is appeared to be something in the chat window, so I'm going to look at that. Okay, yeah, that was only we here. Yeah, I saw that before. Oh, sorry about that. Okay, let's go on and move and talk about multi-column keys. So we're going to continue with this B details table. It has the primary key on order ID and product ID, and the particular table has up to 600 products per order. So let's now say I want to do some operation on that table. I want to do chunking operation. How can I handle this? Well, maybe I could just ignore the product ID and run a top load over the order ID. Well, let's say if I go with chunk for a chunk size of 5 million rows. Hey, what some chunks have 5,600,000 rows. Who cares? Not a big deal. And believe me, you want to stick to this pattern as long as you can, because the alternatives are not really palatable. But however, let's say now that there could be 10,000 products per order, and you must absolutely not exceed a chunk size of 1,000 rows to avoid table locks. You need to be nice to others. Well, obviously, then you need something different, obviously. Now you might think, well, couldn't I just extend that top loop to use 2 more keys? How difficult can it be? Well, let's have a look at that. And I'm going to warn you that the script I'm going to look, it might go a little bit too fast for you, but there is kind of a point for that, as I will tell you later. So anyway, first I got optimally priced simple, which is the same top loop as before. I got the chunk size as parameter. I got the lowest boundary for my chunk. I keep on looping. I got the max ID, the upper boundary. And here, as I said, I don't care about the product ID. I got the operation in this case is really, really silly. I'm multiplying the unit price by a factor of 1.2. and I have option recompile, get the next lower boundary. But now, okay, I want to stay within my chunk size, let's say 1,000 rows. So, okay, update price double. It's trying to take care of both the order ID and product ID. And as you see, I need a lot more variables. I need a min order ID and a min product ID. I need a max order ID and a max product ID, and also stop order ID and a stop product ID, and a game over variable. I start with getting the lower boundary, my first chunk, and I can't use min here. I need to use top one because I want the first order ID, the smallest order ID, and the smallest product ID on that order. And then I also need to get, well, which is the last order ID and the last product on that order. I keep on looping as long as it's not game over. I set these max variables explicitly to null for reasons I will explain in a second. I got this top loop query here now. It's the same one as I had before, more or less, but it's like it, oh well, except I got a row number as well. But select top chunk size from big details, where I'm starting at my lower boundary, and already equals to that min amount boundary, the product greater than smallest on that one, and all the upcoming orders. Take row number because I can't take max again. I need correlated already in product ID. So I use row number, and the row number is equal to the chunk size. I get that is my upper boundary. Now beware, for the last chunk, this select will not produce in the rows because I will not get the chunk size. And when you have a select where you assign the variables, which does not hit in rows, the variables are left unchanged. That's why I set them to null up here. Now, once I've got the upper boundary, well, if I didn't get an upper boundary, this is my last chunk, I say, okay, it's game over, and this is my upper boundary, the stop order ID, the stop product ID. Now, when I'm going to do the update, there are quite a few cases to consider. First of all, did I move on to a new order? Yeah, okay, I did. Then, okay, I'm going to take the remaining products on this first order, and also the first couple of products on the last order, and all orders in between. Notice these OR conditions, not really palatable, is it? I got option recompile here, but maybe also I stay within the same order and do this, product ID between these two. And now, if it's not game over, I go and find the lower boundary for the next one by getting select top one, min product ID, with order IDs equal max order ID, and well, product ID is greater than my upper boundary, and I will find something. Now, when I tested this, performance was not very good, particularly not for the smaller chunk sizes. And when I investigated it, I found that the problem here was the OR conditions. The optimizer did not get the best plan. So I found that I had to go to update price triple, which the difference is to the previous one is that I split up that update statement in 3 different ones because that performed better. Now, as I said, maybe you didn't get all this. Maybe this was too fast paced for you. But in that case, you got the point. I don't like this code. I think it's too complex. This was only 2 keys. You can imagine if we have 3 or 4 keys. So I like to look at other alternatives. So one thing we could do is to define chunks in a temp table. So here, what I'm going to do, I have a temp table called chunks with the order ID and the product ID and the chunk number, with a clustered index where the chunk number is the leading column. And then I'm inserting rows, doing a row number, ending a division by chunk size. So I'm assigning my chunk numbers that way and filling up that temp table. And then I set up a cursor of all those chunk numbers, open that cursor, keep on looping as long as I got chunk numbers back. And then I do my update where big details where it exists from chunks where chunk number equal chunk number and order ID is equal to the product ID and the product ID is also matching. Now, quite important thing here now, the clustered index has the chunk number as the leading column and the clustered index keys of the target table as the next keys. And I also assigned the row numbers that way. Why is that important? Because this means that here I'm updating now an adjacent set of rows physically, or well, in some point physically in the table. And SQL Server has optimizations with this case. So this is faster. I also did a test where I assigned the chunking just so they were by product ID, whatever it was. So they were scattered all over the table. And it was, I think, 3 to 4 times slower. So it's really quite important to do it this way. Now, this was not as fast as the triple top loop. The best case, it was only 1.3 times slower. And the worst case, it was 5 times 6 slower. I think in that case, the optimizer did not make the best choice of plans. I like to add the caveat that the profile of the table is going to matter a whole lot. So if you try this on your table at home, you might see different results, but you would see the same thing. I don't think we'll ever beat the triple top loop because clearly we are sacrificing efficiency for simplicity. Now, this was the big temp table, but we can also do the small temp table. What do I mean with big and small? Well, so the big temp table, what you saw, has as many rows as the actual table, but it's narrow. Let's say the big table maybe has 50 columns, but this one only has the chunk number and the primary key, so it's narrow. So it's smaller, but in terms of bytes. However, to fill it up, we need a full scan of the table, which could block writers. And that could be a bad thing if we are working in a live system where there's constantly rows being written to the table, and we don't want to block those writers. So this is absolutely not always a good solution. But I still like to show you this technique because it's simple. It's simple. You can't really go wrong with this one. It's quite easy to do right in terms of functionality, because the most important thing is that your chunking solution is producing the correct result. But an alternative is the small temp table, which you fill up one chunk at a time. It's more complex, but I think that's as complex as the triple top loop, and it's leaner than the big temp table. So what I do here now, this is slightly different. I got a current already, which is not a boundary for my chunk. This is rather the upper boundary for my previous chunk, and the last product ID is also the upper boundary for my previous chunk. On the first chunk, there is no previous boundary. And I also have a row code variable, which I initialize to my chunk size. I'll create my temp table. Now, only with already and product ID, I get my current upper boundary, or my previous upper boundary as well, and already below the smallest already in the table. And I keep on looping as long as I have my chunk size is being fulfilled. I clean up my table. I do that. I like to clean up things at the beginning of the loop. And then I fill it up with a top query. So I'm saying here, order ID is equal to the current order ID, and product ID is greater than the upper boundary of my previous chunk. And the first one, this one is null, but this one doesn't hit in rows. And also order ID is greater than the previous upper boundary. So I'm filling up a chunk here. I'm capturing how many rows did I get. So if I didn't get chunk size, this means that it was the last chunk. And then I do my update, and again, here adjacent set of rows. And then I get what was actually the upper boundary of this chunk. So I get top one query, order by descending, product ID descending. When I tested this, well, compared to the triple top loop, it was still slower, between 1.3 to 3 times slower. Compared to the big temp table, it was, well, up to 5 times faster, but in a few cases, slightly slower than the big temp table. This script is the same script I showed you before. You can see the complete procedures for the small and big temp tables, and also the variation where I had a different scattering, a different way of filling up the big temp table, and you can see some performance data that I put in. So now let's talk about the application impact. If you don't do chunking, well, everything's one transaction, which means that the application will see, well, either the entire transaction or nothing at all, or be blocked, or whatever. Unless, of course, you're doing no log. No, please don't do that. Don't do that, because then you're really playing lottery with your data. You might get completely incorrect results. I hate no log, most cases. But anyway, so this is not a problem. But now if you split it up in chunks, so the application may now see data that's been processed halfway. How will the application behave? How will the users react when they see this halfway processed data? Halfway processed data. And this is even more pronounced if your operation is interrupted, either by accident because you run out of disk space, whatever, or purposely because maybe you know that this operation, I can only run this between 2 and 5 o'clock in the morning. So I have to split up running over several nights. Well, maybe you can shrug your shoulders because maybe what you're doing, you're initializing a new column which is not being exposed. Or you have to make substantial changes to your application. And that may be very likely if you have one large operation today that you want to split up in chunks. I can't say what you should think about and what you should do. Or I can't say how you can identify these things, but you need to think about this. Could there be some problems with doing splitting up chunking? Now let's talk about resuming chunking. Your chunking operation is going, and then for some reason the server crashes, or you purposely only have scheduled to actually restart. What am I going to do to resume the chunking? What can I do? So I'm going to look at 4 canonical scenarios. How I'm going to deal with this. And the first thing is a purging operation. And what I'm going to do in the big trans table, I'm going to split operations that are older than purge date. Before I'm going to discuss restart, this is one more chunking pattern. So in this table big trans, there was no index with transaction date as the leading column. So I can't just simply do delete top with transaction date less than purchase date, because then I could get table scans. So what I'm doing here is I'm defining chunk number but with integer division. So I'm creating a big temp table, except I'm not keeping that temp table, because all I'm then going to do, I'm only going to do this as a drive table, and so it only exists temporarily, or not, maybe not even that. And then I get the smallest and biggest transaction ID for each chunk and set a cursor over that. And then I run my cursor, max ID, and here is a very simple query to do the purge, option recompile. Now is the question, this procedure stops, I need to restart. What do I need to think about? Well, basically nothing at all. What has been deleted has been deleted. I can just continue. Now, here's insert top plane. This is the one we looked at before. I'm copying data from new trends to big trends. Oh, sorry, from big trends to new trends. Now, if this one is interrupted halfway through, can I just restart? No, of course not, because I'm going to start with trying to copy the first transaction ID once more, so I will get a primary key violation here. No, that's not going to fly. However, the fix is very simple. I can just say, okay, I'm first going to look at new trends. If there is a transaction ID, I'm going to assume this is where I'm going to start over. So this was a quite simple case. Now, update absolute. This is the case where I've added a new column to a table, and now I want to initiate it with something. So here I'm doing again this top loop, selecting top chunk size. This time I'm using the dynamic scale. And well, if this one is interrupted halfway through, can I restart? Yes, I can, assuming that I know that this sum value will always be the same, either because it's a constant, or I'm assuming that my queries will always, that I use to initialize this, will produce the same result. But it also means that I'm going to redo work. So it's not very efficient. I can speed it up a little bit by having this condition where new call is null, but I will still have to go through all that data and scan. So maybe then it's better than to just say, okay, give me the smallest order ID where I was, so I can start over from where I was and be a little more efficient. Now, update price, simple. This was the one where I multiplied the unit price by 1.2. So this is, the previous one was an absolute update. This is a relative update. Now, if this one crashes halfway through, what do we do now? Think about that for a few seconds. I got some water. Well, let's not. There is a very, very special pattern with the prices. There's only one choice: restore and backup. And we don't want to go there. We don't want none of it. We want to avoid that. So we need to be a little more clever. So here is update price pursuable. So what I do is I first check, does this table exist? Guest.last ID. If it doesn't, I'm going to create this table. It's a one row, one column table. And I'm going to add the smallest order ID minus 1 into that table. And then I'm going to start and pick up that last ID plus 1. So that's the starting boundary for my next chunk. I keep on looping. It's the same pattern as before, updating the price by 1.2, but it's a transaction, and I save max ID to this table. And at the end, I drop it. Now you might think, what is this guest dot? So the guest schema exists in every database, and you can't drop it. So I kind of like to use that for a kind of temporary table. Except, yes, this is a sort of temporary table, but it can't live in TempDB because it must survive server restarts. Now, if you think it's too fancy to put in a guest, doesn't bother. The important thing is it must live in the database itself. Now, let's look at this pattern at some of the other operations. So this update absolute here. Let's say this is a really big operation, this is a really big table, but I can only run this between 2 and 3 o'clock in the morning, because even if I do small chunk sizes, I'm still going to load the system too much. So, and then if it takes 5 seconds here to do this, to get this min ID, let's say 5 seconds, oh, sorry, 5 minutes to find this min ID. I mean, that's kind of stupid. Maybe then I should just save that one to a table so I can start off directly. And maybe then I can complete in, let's say, 8 days rather than 9 days. Or this purge operation. So here, let's say I have to interrupt this one. Again, I can only run this between 2 and 3 o'clock in the morning. So maybe then it would be smarter then to have a permanent table where I write these pairs of IDs. So when I start over, I can just go pick up where I was, and only when I've exhausted that table, I fill it up again because maybe purge state has moved to a new date. So to repeat, I looked at these canonical scenarios. So one possibility is just to ignore and start over. You can do that very well with purges and also absolute updates, but then you will redo work. You can find logic in your operation to find out where you were, like finding the last row when you inserted. That's quite simple. Or you can add a more general solution, is to add a help table to track where you were, but not in TempDB. It must be in the database itself. Or if nothing else, if you're not sure, you have to restore backup. And I showed you 4 canonical examples. Your real operation may be a lot more complex. Maybe you're calling a still procedure that you don't know exactly what it does, but you're sending in lots of rows at once. And the less you know about it, the more likely is that you will end up here if you do not plan ahead. There is one more option though. If I do the chunking inside a transaction, there's not a problem, because if it fails, it's going to roll back. Wait a minute, that's completely crazy. Didn't we introduce chunking to get rid of those transactions and keep the transaction log in check? That's true, but there is another reason to do chunking that I haven't mentioned. You could have the issue that you have a query plan where the performance does not go linearly. So let's say this, processing 1,000 rows takes 50 milliseconds, processing 10,000 rows takes 2 seconds, 100,000 rows takes 40 seconds, etc. Or it could be that it goes linearly to some point and then starts to spill the disk, and the transaction performance, execution time goes through the roof. Now, of course, the best thing might be to address that query, but for some reason that could be quite complex. It may not be feasible. So, but then still might seem very far-fetched to you. Well, believe me, I've encountered this situation. What I was doing, I had a procedure that was going to collect well, some fees from a number of accounts. So it actually found 140,000 accounts to levy this fee for, put them in the table, sent them into a superprocedure. It was a general superprocedure to create transaction in our system. That superprocedure had a join between 2 table variables that was optimized for 1 row in each, and the transaction plan was not good for 140,000 rows. And that procedure was used in quite many places in the system, and also in different ways. Lots of things where we actually send quite a few transactions in the kind of a loop thing. So I was a bit nervous to just change that on the web, because after all, it had been like that for over 10 years. And so what I did was I did do chunking inside the transaction in my calling procedure, because removing that transaction would have a lot impact on the application. I would have to think about a lot of things to cover that up. Now let's talk about the risk for bugs. Introducing chunking means that, well, increase complexity. So if you're coding casually, sleeping and doing more like this and sitting in the keyboard, yeah, you could introduce silly bugs like, well, skipping a row between chunks, or process the same row in 2 chunks, or miss the last 2 rows. So I would recommend that you do this. Test your data set on small, different chunk sizes, like the last chunk, fold -1, the last chunk exactly full, the last chunk exactly 1 row. Yes, I showed you a generic pattern, but I know you're going to deviate from that pattern every once in a while, because it's going to make sense for your particular situation. Review your code, have someone else to review it, and if it's possible, add assertions. Like if you're copying rows from one table to another, well, just do a count of both of them. Did I get the copy of the same copy? Do I have the same amount of rows of both of them? And performance, yes, you need to test for performance as well. But here's a really big challenge. You cannot test all possible variations. I know, because I ran lots of tests for these presentations, a lot more than I've shown data for. And it took quite some time for my small tables and my small database. Basically, you have to restore the database every time, because you have the same situation. So testing everything, it just takes too much time. So you more or less will have to make a choice from gut feeling, but you need to test that gut feeling so you don't run into a disaster. And that is also the key. You're not looking for the very top best performance. You may not really care whether it takes 96 or 120 minutes, but you don't want it to take several days. You want to stay clear of disasters. And also, don't look only at the execution time, also monitor log space and temp DB consumption. So the last thing I like to talk about is how we can use a chunk to handle errors. So something, all or nothing, is not what we want. Normally, when you do, let's say, an update statement or insert statement, if one single row is bad, if there's a single null violation, not null violation, for example, everything is rolled back. And in many cases, that's exactly what we want. That is kind of the joy with the set-based statements. But let's say this, we get 45 orders on the file from some source that is not really in sync with our system. So that could be products we no longer have in our system, or that could be a customer that is blacklisted, or something else that is wrong. So we don't want that order in our system. But let's say there's 4 bad orders. We still want the other 44,986 orders so we can make business from them, so we can serve those customers. So we really need to process 1 order at a time then? No, divide the orders into chunks. So if there is an error in a chunk, redivide those into smaller chunks and retry. And trap the errors again, and eventually a few orders will be processed one by one, but not all of them. So let's look at this, and I'm going to unplug numbers are going to be a little bit too slow.
Orlando?
Yeah.
I can, okay. Now,
Yeah.
now I heard you.
Yeah. Yes. I took up the camera, and I hope I'm
the camera, okay.
Yeah, I did this because else the this one is gonna run a bit, gonna take a little too long time to run those demos. So I'm gonna start this script. This script is just a simple-minded loop. So I'm gonna start this and talk about it. So I'm collecting where I started, how long I've been running, how many rows I've been processing, the current order ID, and the cursor. So I set up a cursor, or I got a table called new orders with 4,000 to 5,000 orders. Setting up a loop, keep on looping for taking the one order ID, start a transaction and the try block around it, inserting into big orders and into big details. There's also new details tables, doing commit, and here I'm trapping an error. So if I got an error, I will roll back the transaction, capturing the error message, and I'm raising an error here. I would probably not raise an error in the real world case. I would probably log to a table, but this is for the demo. And then I just adding the row by number 1, and if I pass 1,000 rows, I do a raise error now with level 0, but I use raise error with no weight so I can see how long I've been going on. And then also at the end, how long time did it take? And I will also delete the orders so I can start over. And let's see now how this one is still running. And you can see there was an error. So at some point there was more errors, and yeah, okay. It's only halfway through, or more or less. This is because the GoToMeeting software is taking quite a bit of resources for my laptop. Uwe Ricken had the same problem in his session earlier today. So we just need to have some patience. That's why I took out the camera, because with the camera, probably takes even more resources. Yeah, but thankfully this is the last session of the day, so I will not run over and hurt someone else's session. Normally this completes about half of the time. Yeah, and this was the last order that failed, and now the whole thing is done at 108,765 seconds. Now let's go to the other script. And so this one I'm doing chunking. So I've got a start time, how many times I've been running, and the chunk number and the row size. And here I've got a temp table called temp orders, and this is a so-called big temp table with a chunk number and an order ID. And this here I've got the filling it up by taking the order ID and integer division. Here I'm hard coding the chunk size to 10,000 and doing -1 so that every chunk has 10,000 rows except for the last one. So filling this one up. I do not use a cursor here because my chunk numbers is going to change. So therefore I'm doing an exist. I like to use cursors as long as possible, static cursors, because that's the best way to do a loop. But that's a different presentation that I have. So anyway, my while block, I got a try block for the entire while loop. I'm getting the next smallest chunk number, the next one to process, start a transaction. I'm copying all the rows for this chunk from new orders. Here, temp orders, order ID equals chunk number equals chunk number, capturing the row count, also copying from big details, commit the transaction, and here I'm doing a raise error with no weight, but level 0, so this is just diagnostics, and I'm deleting that chunk from the work table. And here down in the catch block, well, I roll back the transaction, I capture how long is the chunk size? What chunk size do I have for this one? And if the chunk size is bigger than 1, well, then I decide I'm going to redivide to smaller chunk size. And this time I divide by 100. I say the new chunk size is equal to the chunk size -1, divide by 100, integer division, remember that, +1. And I need to do this -1 and +1 so I don't get 0 for the chunk size. And also printing out that it did this redivision. And now I'm going to compute the new chunk number for this one, or the new chunk numbers, I should say. So I got the CT, getting the chunk number, and then I'm doing row number, order by order ID -1, and integer division by the new chunk size. So I'm getting temporary chunk numbers here. And then you might think here, I would join the CT to the temp table, but I don't have to do that. You might not have seen this before, but you can do an update on the CT itself, and it will map through to the temp orders table. That's quite neat. It's quite scary when you see this the first time, but it's really, really neat. So I take the temp chunk number and add the max chunk numbers +1 to get the final chunk number. Now, if the row chunk size was 1, this means that this was a bad order, and I'm getting the order ID and raising the error, and also deleting it from the chunk size table. And at the end, I'm going to do the same things before. And I'm going to run this, and it's probably going to be a little slow, but hopefully not as slow as the other one. So anyway, this one chunk went well. This one had errors, apparently. It was redivided. This one had errors. This one went fine. This one also had errors. The last one, now we're getting lots of chunks. This one also had problems because it was redivided. We have lots of chunks now running on the size of 100. So it's processing. And yeah, here's one more that had errors. And we're going to keep on rolling here. Now we can see chunks that are in the size of 50 because of the last original chunk. And we keep on rolling here, and we will eventually get to those where we have one orders at the time, and we should see some error messages. Yeah, that was one error message. And now, well, there's one more error message, and it has complete, and I think there's one more error message towards the end. Yes. Anyway, it completed now in 32 seconds or 33 seconds compared to this one. That was 108. So by doing chunking, we slashed the execution time with a little more than a factor of 3. Now, when you're going to do this, one challenge is to find the initial chunk size. Because keep this in mind, if you set the initial chunk size too high, well, then about every chunk will error out and roll back. And of course, that's not efficient. So what chunk size should you pick? Well, this is my rule of thumb, and it's not based on science. It's not based on tests. It's not based on math. It's just gut feeling, just taken out of thin air. Well, or common sense is maybe a better word. So if you expect one row out of n to error out, well, set the initial chunk size to n divided by 10. And of course, assuming no other limitations, like you have to be nice to others. You may note that in my test, I had 10,000 as the chunk size, but a little more, well, almost one row out of 1,000 error out. So I should, sorry, one row out of 10,000 error out. So I should probably have a chunk size of about 1,000, 1,500 or something like that. So I probably had a big 2 chunk size. So now, determining that n may require some quite good gut feeling. Oh, of course, if you already have a process in place where you're doing one by one and you want to improve it by doing chunking, you can probably find data of how common errors are. But if you're setting up a new process, well, I would say make some reasonable choice and then monitor, see how it works. Maybe your chunk size is too small, maybe you get too many errors or rollbacks, then you have to decrease the chunk size. Also, think about this. Do the errors come in bursts or are they scattered? Because maybe your source is like having a bad day, so that you get lots of errors at the same time. And in that case, you can probably go with a bigger chunk size than if you have complete the random errors. And then how much you're going to redivide? Again, no science, no math, but I would say by 100 or 10,000 at a time. I remember one case where we did this. We had a process that was doing one-by-one processing that was way too slow. I wrote the spec and a colleague, he implemented it, and he did a chunk size of 1,000, and he said, well, if there's an error, I'm going to just do them one by one. And I think it worked out pretty well. So I'm almost done. I was going to do a quick summary of what I've been talking about. So chunking, this is nothing you'd use every day. It's a trick you have in your toolbox for large operations to keep the transaction log on Temp to be in check and to avoid conflicts with the rest of the system. Make sure that your transaction log backups running when you do these operations, because if you haven't, it's not going to help with chunking. You're going to explode the transaction log anyway, unless you're in simple recovery. And indexing is absolutely critical. Your chunking must always follow an index, preferably the clustered index, because repeating scans is extremely costly. The top method is a very generic way to drive the chunks, and it works with any data type you can put an index on, and it even works with non-unique indexes to some extent. Now, if you have multi-column keys, we'll only work with that second level if you really have to. And if you have to do that, well, defining chunks in the temp table is less efficient than extending the logic of the top method, but it's so much simpler. And I showed an example with 2 keys. Let's say you have to use 3 or 4 keys, then it's a nightmare to write that, I would say. And also, don't forget to make interval variables known to the optimizer with either option recompile for big chunk sizes, or for smaller chunk sizes, it's probably better to do dynamic scale or some inner procedure. And in that latter case, you may have to make sure you have full scan statistics. Or find some other clever way, but maybe you start in the middle so you know that you're inside the histogram when you sniff the plan. Don't forget to consider how the applications will be affected. Don't do that. And I can't say in what way, but you need to think about this. Design your loops so they can restart where they were interrupted. You may not have to code for this exactly, because if it's a one-off operation, but you don't really have to code for it, but at least you need to have a plan. If the thing stops, what can I do to restart? Because you don't want to restore a backup. And if needed, create a help table to track where you work. And don't forget the test for correctness and for performance. So my name is Alan Somasko. My email address is there, sql@somasko.se. So if there's any questions that I don't answer today, please feel free to mail me. Oh, there's one more thing I like to say. I have basically only scratched at the surface of this topic. There's so many, I mean, we don't do this every day, so how can we know all the tricks we can do? I found out quite a few things when I was composing this presentation and making scripts and demos. So if you make some interesting revelation, please share it with me. I will be very interested. So slides and scripts for my presentation are available on my website, somasko.se/present, and the BigDB database, you can find it here, bigdb.back, and it's 3 GB in the download. It will expand to 20 GB. It's a compressed backup, and you need at least SQ 2016 or later. Thank you very much for listening to me. And any questions, I'd like to answer them.
Thank you for your great session.
That's
there is no.
Yeah, I saw a comment from Tommaso. He was.
There aren't questions for you.
Yeah. He was just giving his appreciation. Well,
we hope to meet at the next event in a non-virtual way.
Yeah, I'm looking forward to that one as well.
And there isn't a question, so the session is closed. Thank you very much.
Thank you.
And see you later. I hope.
Yeah, thank you very much, Marco, for arranging this. It's been a pleasure to talking to you, and I hope you enjoyed it.